You mentioned a few minutes ago that the standard model of particle physics is couched in quantum field theory.
Hmm.
And one last sort of conceptual question I want to ask before we moved more toward introducing the search for the Higgs boson is just what the relationship is between the standard model and quantum theory as it was formulated by like the 1920s or so, because when we hear about things like the interpretations of quantum mechanics, like I already mentioned, none of this comes into it. We're not talking about the Higgs boson or uh, gravity or anything like that. So I'm just wondering what the relationship is between the two.
So one of the relationships is that when quantum theory initially, I mean, it's the theory you need to describe subatomic physics, and that means really fundamentally to describe electrons and photons is probably the first thing you hit. So why do atoms um, emit light and absorb light with particular frequencies and things like this? And that it's the kind of the Bohr atom. It's the fact that there are only certain discrete allowed orbits or bound states in an atom. And that just forced people into this idea of a theory that's kind of probabilistic, and you start talking about wave functions and things. That was then taken together with relativity, really, by Paul. So that was the theory of Heisenberg and Schrödinger, I guess. And I'm not a historian, so I'm probably going to get some of this wrong. But this is the way physicists, the way it looks when you're doing an undergraduate physics degree, maybe, or a PhD. But that was the kind of world of Schrödinger and Heisenberg, loosely speaking. And then you bring that together with Dirac brought that together with special relativity, actually. And this is one of the, I don't know if anyone's talked about this on here before. This is one of the moments in physics when you're learning physics, and you think this is amazing, and it really happened. Dirac was trying to write down the equivalent of Schrodinger's equation, but rather than using the Newtonian relationship between energy and momentum and starting from there, he started from Einstein's relation in special relativity, so E equals mc squared essentially, and tried to make it. Basically, had to get rid of the square. If you tried to make that a quantum mechanical equation, he ended up with negative energy particles, and of course, negative energy states, everything would just fall down, 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 down into the lowest energy state, and the universe would be unstable. So that had to be wrong. So he said that's because it's a first order equation. It has a square root. It's really this simple. It has a square root, and with a square root, you get a plus or minus, and the minus is a big problem. He said, right, I have to make this a first order equation. And to do that, you have to pull in some really weird algebra where a times b doesn't equal b times a, because otherwise the equations don't work. He kind of forced it. It feels like you think of the logic. It feels like you're forcing a square peg into a round hole. You're really, contorting your logic. Anyway, he came out with the Dirac equation, which did two things. I mean, it worked for a start. It brought relativity and quantum mechanics together, but it also explained what the spin of an electron was, which we knew about but was puzzling people. This is kind of in the 30s and 40s, 30s, I think. And then it predicted the existence of antimatter as well, which no one had even observed, and it just seemed ludicrous. And within a few years, they actually found the antiparticle of the electron. And I know it sounds like I've digressed a little bit there, but this led to this formulation of quantum field theory, where you have the possibility. So it's grown out of the Schrodinger's equation or Heisenberg's uncertainty principle, all the stuff of the early quantum mechanics. They're still good. They still work for a lot of things. But you get this quantum field theory where you have the possibility of creation and annihilation of particles because you've got matter and antimatter in there as well. And then I guess that was then the bedrock on which Feynman and Schwinger and Tominaga built quantum electrodynamics, which is the first kind of complete quantum field theory. So there's a clear progression from this. And all of that still is dealing essentially with electrons and photons. And then to get to the standard model, it's basically taking what Feynman and mainly Feynman's language is what we use, but it was independently developed by Tominaga and Schwinger. And it's taking that language and extending it not to just understand electromagnetism, but also the weak interaction and the strong interaction. And that becomes a standard model. And then at that point, you realize you have a problem with mass, and then you have to bring in the Higgs boson there as well. So the language that they're all discussed in is basically the same language as quantum electrodynamics, which came from Feynman, came from Dirac, came from Schrödinger and Heisenberg. So there's a clear path through in the maths, and there's things that are similar throughout them all. And the standard model is really then saying, okay, but there are more.